breaks are too short and class is too long. Yes?
Sorry, you said that the mux has to provide us with 0, A, or minus A, right?
Or A bar.
Yeah, A bar. But we assume that when
This is A bar,
yeah,
this dot, it's the inverter.
yeah, yeah.
This is A,
A.
and when I'm not enabling this guy, he's getting a 0 down. It's a different kind of mux. It's not a standard one, but won't be. I have an extra kind of control for it, but it's not such a big deal. You know, and also it's good to have imagination. It helps you grasp the concept. No, but in practice, this is easy to implement. More questions? No, that's good. Now, there is something which I observe, and that one is that whenever the bit of x that I'm processing is 0, I'm kind of wasting my time. I should not do any addition. Then I just, you know, should do a shift and I'm done. Because there is 0 added with the previous value, and then I'm wasting time in here. Now, you know, if I speak about synchronous designs, I always have to assume the worst case. And the worst case is that all the bits in X are 1, then I'm always doing something here, addition or subtraction. But in general, those are 0 and 1. There is a equal, okay, 50-50% probability to have 0s or 1. Except if you deal with some kind of special applications. There are data processing applications where you know the profile of the data and you know that there is kind of biasing towards some values. And you can take advantage of that in designing a better multiplier, cheap and faster. And some time ago, when we were not that much in asynchronous design, the idea was to try to increase the number of zeros, because whenever you have a 0, you essentially have a shorter cycle. You just skip. This is good for asynchronous. When it's synchronous, remember, I always have to wait for the clock to come after the worst case situation. I keep on saying that, and some of you might get bored by this remark, but I know from experience that it's good to mention it. Now, and speaking about special data profile, this is in audio signal processing. This may be quite probable. Now, this is called booth recoding, and the idea of booth recoding was to preserve the value and to increase the number of zeros. Remember that we could add or subtract. Then the fact that a bit was a 0 or a 1 was not a restriction. A bit could have been also a -1. 0 is nothing, 1 it's an addition, -1 it's a subtraction. Then I can allow for having bits in my X which are with explicit sign. Now, what will be my idea will be to rewrite my X in such a way that I have now 3 values, possible values for Xi, 0, 1, -1. And I am kind of increasing the number of zeros. And this is based on this property, which is saying that whenever I have a string of 1s, I can replace this string of 1s with a -1 in the current position and a 1 at the end of the string, right? 7, it's equal with 8 - 1. 16 is 15. No, 15 is 16 - 1. Then, and this is a property which is okay in, you know, in binary representation, and you can see this is the rule of scanning, and you consider 2 bits at a time. Then what you do, you start from the least significant position and you see a 0, I copy a 0. I see a 1, this is the end of a potential end of a string of 1s. Then I'm writing here a -1. I go further, it's a 1, then it's continuation, continuation, and then this is stopping. And I write here a 1. Then from the point of view of these guys, I rewrote these 3 1s as a 1 and a -1. I preserve the value because this is a 7. If I put the reference here, actually it's a 7 times 2. And this is an 8 minus 1. Then I'm okay. Now I can do that. I have to do it serially. Then it will take me some time. And eventually, I have now a rewriting. If this rewriting will provide me more zeros than before, and I apply an asynchronous design, I will have more chances to skip the addition. In this example, actually this is not useful. I don't count them, but from the bird's eye point of view, there are no more zeros than ones. Then it's not really helping. But this doesn't mean it's not helping at all. Here you have a lot more combinations. Then in some cases, this might help a lot. Now, there is something else because you can get here some kind of extra bit, which is not an overhead, by the way. It's not an overflow. It's just, it's an artifact of this transformation. But this one by itself is not useful today. It was used with the idea to increase the number of zeros and then to increase the number of skips without addition. Oops. Okay, this is a beautiful slide. Probably it's not compatible with my screen. This is a PowerPoint, and I choose for PowerPoint because it was an animation which I wanted you to see. This is an example, you know, you have the multiplier, you have the boost recoding, and now whenever you have, it is really a bad recoding. Because before you had 2 zeros, now you have only ones and minus ones. And then you control the sign by doing addition or subtraction. Look. Now, before, because essentially what we did thus far, it's a very slow multiplication. We just built the concept towards doing fast multiplication. But before getting there, we have to think a bit about multiplication with constants. In many applications, you do that. This is kind, you know, I'm in a matrix and I'm computing, you know, some kind of indexes in the matrix. Then I'm computing pointers. Because the dimension of the matrix is fixed, I have to do, you know, multiplications with constants. And there are two things in here. I can use a normal multiplier, or I can use some instructions in order to do that. The same story will apply for filters, because in filters I'm doing multiplication of an element of a vector with some constants. Then in here I have two solutions. One is to use a normal multiplier and to treat the operand, which is a constant, as it would have been a random value. Or I can treat that in a different way. And I can do some kind of tricks at the software level. Now, why would that be an interesting idea? Because I may have functional units in my processor which are idle, and my multiplier or multipliers are busy. Moreover, I can free the multiplier for other things. If I have an out-of-order processor, then I can do things in parallel and I can distribute the resources in a better way. Now, remember, yes?
And also it's faster to treat the spectrum as a constant of powers of 2.
That's trivial.
It's going to end up only in C.
Then if it is a power of 2, it's just a shift. But it's, most of the time it's not a power of 2. But what you said is correct. I will use some kind of instructions, and I'm emulating that in software. Because my constant is known beforehand, this is the code that the compiler will generate. Then I am doing a shift, an add, shift with 4 positions and an add. Then instead of doing a multiplication, which thus far we saw it takes n cycles, because I have n iterations, then I have a 32-bit architecture. Then instead of doing a multiplication in n cycles, this will take me 8 cycles. Each instruction in here will take 1 cycle. It's a shift, an add, a shift, an add. Then if my multiplier is not powerful, this will be for sure more effective. And I can even do, you see, that's the reason why I don't like animation. And I can even do better things. As a computer architect, I should be aware of that. And then what I should do is I should augment the instruction set of the processor with a compound instruction, which can do shift and add. And then instead of spending 8 cycles, I can do the same story in 3 cycles, which is very close now to what I can do with a very expensive 3 multiplier. You will see that the best multiplier that I can build, or probably you are aware of that if you did some assembly programming, that multipliers today in good machines, they take 2 cycles. Essentially, 1 cycle is in order to compress this partial matrix to 2 rows, and the other cycle is to do the carry propagate addition here. Now, if I have that kind of instruction, I can do a multiplication with a constant in 3 cycles without using the multiplier. Then I'm making a nice balance between software and hardware, and I'm using the resources which are available. The combination of instructions will very much depend on the constant. If on the constant I have a 1, I do shift and add. If it is a 0, it's just a shift. I can also do recoding. Then I can recode this constant in both, which in my case now will help. And I can do this in 2 cycles. Then it's as good as it gets without using the multiplier. Now, and I can also do a factorization of things, then only the sky is the limit. Essentially, this is done by the compiler. Then in early days, we are doing that by hand. Today, the compiler in the optimization loop is doing that kind of things. Now, those are special cases. Now, you can also apply that kind of optimization by constructing a partial product matrix which will skip the rows which are 0, and then build a fast multiplier which now will be a 3 multiplier. But then that hardware is just good for that. And it makes sense to have such a hardware when you have a special purpose processor, like you do filters, and you are not changing the constants. Because if you change the constants, you have to redesign that hardware. Now, what we saw is that multiplication can be done in n cycles, which is not a fantastic result. Then, actually, you could have guessed that before the discussion. Now, how can I go faster? There are essentially 2 solutions. One solution is to do something in order to have a smaller number of rows in that matrix. That's one solution. Then I have here n products. and instead of having n products, if I can get less, this will be faster. The other solution is to do the reduction of numbers in a faster way. And you already know how, don't you? You do or you don't? Come on, you do. We discussed about that in the beginning of the lecture. Then if I apply reduction techniques, then I'm treating this as a multi-operand addition, then I will accumulate the numbers without propagating the carry. What's happening there? No, nothing, they're very quiet. Now we'll go both rows. Now, this is the multiplication in the general case. We did it in Radix-2, and in Radix-2, we had here a shift with a power of 2. If I'm doing in a general case in Radix-R, this will be a shift with a larger power of 2. Then instead of 2 at minus 1, now I will have 2 at minus 2, 2 at minus 3, whatever. And this will allow me now, somehow, to do a better job. But how do I do that? I have to convert my number from Radix-2 in a higher radix. Then if I have an n-bit number and it is in Radix-2, it will take n cycles with sequential multiplication. If I have an n-digit number in Radix-R, it will take again n cycles. However, by moving from Radix-2 to an Radix-R, the same number will have less digits. Then it will be more effective. The same story, I can go from least significant to most, and again, I prefer this one. Now, the big difference between Radix-2 and a higher radix is this one. In Radix-2, for this one, which is a 4-bit multiplication, I have four partial products, which I have to compute, and then add, which is 4 cycles. Now, if I apply the same trick, and now I'm doing Radix-4, Radix-4 means that my digits can be between 0 and 3. Then I can group, remember Radix conversion, which could be done on the fly by just grouping things. Then I can group these 2 bits as a digit in Radix-4, and these 2 bits as a digit in Radix-4. Which means that instead of 4 rows, I have 2 rows. Then I won, right? It's true, however, I have a problem. While generating the partial product in the first case is just copy of A or 0 or minus A, in here I have to really multiply this with A. Then this can be 0, A, 2A, or 3A, depending on the value in here, which will complicate the work. Now 0, it's simple. A, it's simple, it's just a copy of A. 2A, it's simple, it's just a shift. 3A is not that simple, because 3A means that I have to do an addition. Then I make a shift, I compute 2A, then I add with A, and I got 3A's. Then if I manage to do that in a smart way, then I just have 2 rows, which I now can add. Then from one point of view, I have less iterations. From the other point of view, my iterations are a bit more complicated. Now, how can I deal with that? There are a couple of solutions for that. I should go for the PDF. Then, because I'm doing Radix-4, I am looking now at 2 bits at a time from X, right? And I'm consuming 2 bits at a time, which means that instead of having k cycles for a k-bit number, I have k over 2 cycles. There is something else which I should do, and that one will take me one more cycle. And this is the preparation for the multiplication. And the preparation is to pre-compute 3a. A is constant while I'm doing the multiplication. Then in the first cycle of the multiplication, I'm essentially pre-computing 3a. That will take me one cycle. Now, in each and every iteration, I'll do something similar with the previous case, except that now I have a wider max with more possibilities. And I'm selecting 0A, 2A, 3A based on 2 bits, which are coming from shifting X. And I shift now with 2 positions, each cycle 2 new positions. If it's 0, 0, I get the 0, 0, 1A, 2A, 3A, and 3A is available because I spend one cycle to pre-compute it. Then it's slightly faster. Actually, it's plus or minus half time, but it's still not 2 cycles. Now I can think further and I say, okay, why not take 3 bits at a time or 4 bits at a time? Because the more bits I get at a time, the less cycles I have. But the more bits I get at a time, the more combinations I have here. And combinations which are a times of power of 2 are beautiful. Not all of them, but most of them are simple, the ones that I'm doing with shifts. But things where I have to, now if I increase, I have to generate 5a, 7a, 9a, then things are getting more and more complex. And then whatever I'm winning by diminishing the number of cycles may be lost due to the complication that I'm getting there. Now this is again an example which you can go through. Then I'm taking, I'm pre-computing 3a, and then I'm inspecting 2 bits at a time, and with these 2 bits at a time, I'm doing the calculation. You see, it takes less cycles, and I can apply all the tricks that I know. Now, the fact that I spend a cycle in computing 3a is not something that I'm happy with. What I want is I want to have 2 k over 2 cycles with no other overhead. And this is a solution to deal with that. Then instead of pre-computing 3a, I'm doing a trick. Then I am generating a minus a for the current position and a carry for the next position, which is 3a, but written as 4a minus a. Then now I will do selection as before, but that selection will not be directly controlled by the 2 bits in X. It will be controlled by a kind of simple logic which will keep in mind a previous carry. If I had to deal with 3a in a previous iteration, I would have a carry here, and then I have to do a modulo 4 calculation in this. Then I put now an overhead in each and every cycle. Because of that, then the selection will be not straightforward, will go through this kind of logic. And then in here, now I can select 0a to a or minus a when I'm actually looking for a 3a. And if I design this in a proper way, like here, this will work like a Swiss clock. Now, which one is better? This one or the previous one? This one, you think? It is more elegant, and I'm not spending an extra cycle to do the pre-calculation. And from that point of view, you are right. But there is this small logic which is now on my critical path. This may or may not change the reality. in principle, it should not. What else I can do? I can try now to diminish the number of rows and combine that with boost recoding. Then I am rewriting the number based on the same principle in such a way that I will never get 3a. I will get a, 2a, minus 2a, or minus a, or 0. I'm conserving the, okay, this is again not very beautiful. This is the table for recoding. And then I am doing that recoding, which is a pre-processing step. And then now, you know, that was the first part. And now, you know, I'm grouping them and I'm getting this Radix-4 version of recoding. Then I have Radix-4, which is diminishing the number of partial products. Then I have k over 2 cycles. And all my guys in here are reasonable guys. Then I don't have 3a, and I don't have to do the trick to pre-compute it or to do that kind of modulo 4 calculation. But there is a problem because I have to process the x in order to get that recoding. Now you see an example on how you do recoding and how this is working and how this is actually working in practice. Then it is very similar with the previous one, I would say, except that now your logic is kind of straightforward, that you do not keep a carry from the past. You just look at the bits and you do recoding while scanning the multiplier. Then you don't do first recoding and then the multiplication. Then you scan now the multiplier, and because the recoding is taking 3 bits in consideration, you have to look at 2 bits which are your current bits and the previous bit which is the context. You will understand the details if you look in the table, the previous table. Now you take these 3 bits, and based on these 3 bits, you actually determine what will be the input for your adder. Then, first of all, you say add or subtract, which is the carry signal into the adder, and then you will determine the magnitude. And the magnitude, it's even 0, and then you enable or you disable these marks, or can be A or 2A. And that will be inverted or not when it's arriving to the adder. Now, A is simple, you just take A and you pad it with a 0. 2A, it's simple, you just shift add A 1 position. Essentially, it's not a shift, it's a wire rerouting. Then this essentially will give you probably the best solution. If you would have done the recoding first and then the accumulation, then not good. But because you can actually overlap them, this is very similar with this one. Except that in here I have a flip-flop, and because I have a flip-flop, this will be slower. I have to compute here what will be the input of the flip-flop. I have hold time, setup time. Then conceptually speaking, they do the same, but from the implementation point of view, okay. Now, then I managed to to speed up the calculation, and I also get rid of the unpleasant story. But I was not really fast. The reason why I was not fast is because I forgot what we just learned from multi-operand addition. Each of my iterations was slow because I was propagating the carry. But I don't have to propagate the carry, because essentially I can use carry save headers in my calculations. And we'll take it, one take at a time into that direction. Now, I can use carry save headers in many ways. This is a way to utilize carry save headers in order to generate 3A. And this is not exactly a very smart approach, and I would never do that in practice, because I'm still doing the accumulation on each iteration. It's just fixing the 3A problem. And I'm fixing it with an extra full header. Then each iteration, I'm still propagating the carry, and this is the cumulative partial product, which is cycle, it's increasing. I add the previous value with two numbers, which will allow me to form 3A. I make a reduction here, this is a carry save header, and then I do the addition. But you already know this is not exactly a good trick, because why would I propagate the carry here when I don't really need that? Remember multi-operand addition? We said that all iterations except the last one, I don't need to propagate the carry. The same concept will apply here. But the message of this slide is that I can use carry save headers in order to generate 3A, which is yet another way to deal with it. It's not making my addition fundamentally faster. And this is a kind of technique which is doing that. This is an implementation. Now I can do this trick while keeping the partial product in carry save format. It's still iterative. Then I have n cycles or k over 2 or whatever cycles I need in order to deal with the number. That's depending on the radix. However, instead of doing at each and every cycle a normal propagate addition, I will do a carry save addition. Then I am keeping the partial product as two numbers. That's whatever it's here in those two numbers. Then before, what I was doing, I had the partial product accumulated, and I was adding or subtracting A. Now what I have is, I have the previous value of the partial product, which is kept as two numbers. I have the new value of the multiplicand. This is a simple case because this is for unsigned, then it's even A or 0. I do the reduction from 3 numbers to 2, and I store the result back in the partial product register. And I keep on doing that until I arrive to the last iteration. In the last iteration, I really have to compute. The first, n bits will be ready after n iterations, because I'm consuming 1 bit, I'm generating 1 bit. Remember, it was a shift kind of story. But the final n bits are in that format, which is carry save format, which means that in the last iteration, I would have to propagate the carry. Then what did I do and what I achieved? I looked from a different angle, and I was driven by the carry save header concept. I can combine that with high radix, but to simplify and to make it clear, I just look on Radix-2. Then while before each and every iteration I had a shift and a carry propagate addition, now each and every iteration I have a shift and a carry save addition. Then it will take me k minus 1 carry save additions if I have k cycles, and in the final cycle I have a carry propagate addition. And this is essentially the trick behind do it really fast. And from now on, you know, I can do things further. And I can, you know, push things. And I can, you know, there are many solutions for multiplications, and this is, you know, combining carry save multiplier with Radix-4 boost recoding. And what is happening now, it's kind of an interesting phenomenon, is that I am consuming 2 bits at a time because this is Radix-4. If I consume 2 bits at a time, I have to generate 2 bits at a time. You know, I have to have a bit flow in my calculation which is coherent. If I'm not generating what I'm consuming, then I have a problem because I have to store. Now, before, when I was doing the calculation, those 2 bits were explicitly ready for output. It was 1 bit ready for output or 2 bits ready for output if I was doing Radix-4. Now, because I'm doing this in carry save format, when I report for output, essentially I report part of this number in carry save format. And I am reporting something like that. You know, I get 3 numbers, which is previous partial product plus the new number. I'm doing the accumulation and I do the shift. When I do the shift, I have a solo bit and I have 2 bits which are like that. And now I have a small problem. If I want to report for output, I have to do an addition here. That I have to, this it's okay, it's good, and this has to be added, which means I will have to generate a carry and keep it for the next iteration, because this will generate a carry here. Now, because it will be a carry from the previous position also, actually what I have is a 2-bit addition. Then I am combining carry save adders with high radix. And now each and every iteration, what I have to do is that kind of addition here and a 2-bit adder to report for output. Now there is a beauty of this, because I don't really have to wait for this to complete before I go into the next iteration. Then this can be hidden. Are you still with me, or I lost you on the road? Should I repeat? Or not? Yes, no, maybe. Maybe is the right answer. You know, you assume full responsibility for the feedback. Huh? Okay, if you don't say anything, I'll repeat. Then this is essentially assuming that each and every iteration, I'm not propagating the carry. And I do Radix-4 work. I do Radix-4 work combined with both. The both will give me the value that I have to add here. We should not care that much about it. But there is a new value coming. There are 2 values from the previous accumulation. I reduce them to 2 numbers. And remember, those 2 numbers, they have to be shift out. I do a shift. Now, those are okay when I shift them, and before they were solo bits, because the carrier was fully propagated. Now there are no solo bits. When I'm moving out, I'm actually moving 2 positions, right? It's Radix-4. Then those 3 bullets will be out. This is an implicit calculation. It's not really giving me bits which I should store in a normal register. In order to deal with that, I have to do this 2-bit addition, which is a simple addition. I will do it with full adders or with a lookup table, whatever. That will bring me also a carry for the next because when I add those guys, a carry may come here. I have to keep it for the next iteration, because in next iteration, I'll have other 3 bits going out. It's always 3 bits due to the nature of this reduction. The first full adder here will generate some carry, and I'll have no carry here. Now, this is coming from the previous calculation, and then I have 2 bits, which are those 2. I have the solo bit, which is coming from the carry. I have the previous carry, and here you see extra dot. Okay, I didn't mention that not to complicate things. This extra dot relates to the case when I even have a sign, and I'm adding or subtracting. Then this may compensate for the negative value, but forget this in order to concentrate on what we have now. Then my process in each and every iteration, it's 1 carry save addition, which is a full adder delay, plus the propagation for output of those 2 bits. Now, when I'm ready with this forget it, because this is for the last cycle. It's the final propagation for the last cycle. I don't care for it. When I'm ready with this, I can go back and process the next one. What I have to be sure is that whenever the new value coming in here, it's available, the previous value is out. Then the cycle time will be determined by the time of the carry save adder, which is 1 full adder plus the both recorder, or by this 2-bit adder. One of them will be slower, and that will determine the cycle time. Now, if I'm doing Radix-4, this is 2 bits. If I'm doing Radix-8, this will be 3 bits. Radix-16, this will be 4 bits. Then eventually, if I push my luck towards a very high radix, this may dominate the calculation. Also, if it is higher radix, then I will have to have here maybe more levels. Okay, this is the recoding principle for this scheme. And this is the extra dot in column I, the one which is telling me whether or to add or subtract. Now, yet another design, right? I'm not doing both recoding, I am just relying on the calculation of 3A based on multiplexers and full adders. I'm taking 2 bits at a time because this is again a Radix-4 calculation. I'm generating 2 bits at a time, but now I don't have that problem with the hot carry because this is not both recoding. Then I have these 2. I have the adder as before. I have an extra level of carry save addition. Because instead of doing both recoding, what I'm doing now is I'm forming the new partial product with combination of 0, 8 to 8. What you see is that I have this guy, which is combining those 2. Then in here I can get 0A to A3A. I have one of the values from the partial product, the previous accumulation, also taking part in here. And the result plus the other one will take part in a final compression. Then I have what is called a 4 to 2 counter. And I have a 4 to 2 compressor. If I can implement that compressor in a nice way, this will be probably faster than the previous solution. Then what I did in this design is that I replaced the boost with the creation of 3A via multiplexers. Then my trade is 1 full adder delay, which is this guy, with the complexity of the boost recoding logic. Now, which solution should I choose? Let's look at this, or look at this, where the logic is something like that. Which one do you like? Yes.
What is the cost of encoding?
The cost of
Encoding.
encoding.
Encoding. Yes.
You know already,
Ten
right?
cycles, so I would say.
A couple of gates. You just have to inspect 3 bits. Then you have 3 bits as input. It's like a truth table, which based on these 3 bits is giving you 3 output signals. Then there are 3 functions which are 3-bit functions. Then you have 8 possible combinations. Then which one do you think is better? And then you can go home. But you don't leave the room before you tell me which one you like.
I go for recording.
You go for?
Recording.
You go for recording. Why do you go for recording? You know, come on, you know, I may say I like that, but I also have to explain why I like that.
I think carry save order with like the number goes and bits. The cost of CSA is, I think it's bigger.
Is that true? I will go for this solution. And the reason why I go for this solution is because this is more regular and because this is actually a 4-to-2 counter, which I know how to implement pretty fast. But that's a matter, you know, of taste. Okay, guys, I had enough for today. You said Wednesday we will discuss the second homework. We will try to solve it.